nuclear physics breakthrough. The origin of magic numbers explained for decades, nuclear physicists have puzzled over magic numbers, specific counts of protons and neutrons that lead to exceptionally stable atomic nuclei. Now, a team led by Jiangming Yao at Sun Yat-sen University in China has resolved the long-standing mystery, connecting these numbers to the fundamental interactions within the nucleus. This discovery bridges a gap between simplified models and complex quantum reality, offering a more complete understanding of nuclear structure. The history of nuclear stability, the phenomenon of magic numbers, dates back to the work of Maria Goeppert-Mayer in the late 1940s, who first observed that nuclei with 50 or 82 protons or neutrons are unusually stable. These numbers, and others like 2, 8, 20, 28, 50, 82, and 126, consistently appear in the most abundant elements in the universe. Early theories explained this stability by proposing that protons and neutrons occupy distinct energy levels, or shells, within the nucleus. However, this model treated particles as independent entities, a simplification at odds with our understanding that they interact strongly. Bridging theory and reality, Yao's team took a different approach. Instead of relying on experimental input to refine shell models, they started from first principles, mathematically describing the interactions between particles within the nucleus with unprecedented detail. Their method involved simulating the nucleus at high resolution, then systematically blurring the calculation to mimic lower resolution models. This process revealed that the stability arises from changes in the symmetry of the particles' quantum states. The key insight is that nuclear structure looks different depending on how closely you examine it. The team's simulations showed that at certain resolutions, the symmetries shift in a way that naturally leads to the observed magic numbers. A mathematical microscope, Jean-Paul Ebrin, at the French Alternative Energies and Atomic Energy Commission, describes this work as a mathematical microscope that mirrors how experiments work. Nature looks different depending on the resolution at which you observe, he explains. The researchers' approach aligns with experimental observation, which always involves approximations and limitations in precision. Further, the symmetry changes identified by the team are linked to effects predicted by Albert Einstein's theory of special relativity, solidifying the connection between nuclear stability and fundamental physics. Future implications: the researchers have validated their model by testing it against doubly magic tin nuclei, 50 protons and 82 neutrons, and other stable isotopes. Their next step is to apply this framework to heavier, unstable nuclei, as well as the extreme conditions found in exploding stars and neutron star mergers. Understanding these processes will provide critical insights into the creation of heavy elements in the universe. This breakthrough doesn't just resolve a decades-old mystery. It provides a new theoretical tool for exploring the most complex realms of nuclear physics. By connecting microscopic interactions to macroscopic stability, this work paves the way for deeper investigations into the building blocks of matter itself.